All right, let's go through a few concepts with regards to what we were going through for the past week or so. The first thing was angles, and we were looking at circles and different kinds of angles in circles, and maybe questions around that as well. Let's see if I can go back to the first part, which is, let's say I draw a circle. Okay. Let's just make a list for now. Let's make a list of all the different theorems. The first one you got is angles in a semicircle, which remember involves a diameter and 90 degrees. And the other triangles in a circle was the tan chord theorem, the tangent chord theorem. The tangent chord theorem, you have a circle and you have a tangent, and at the point where the line is a tangent to the circle, a triangle is formed. And what we have to do now is remember that the angle between the chord and the tangent is equal to the angle in the opposite segment. And that applies on the other side as well. So if you got alpha over here, you can see it would be alpha there. That's tan chord theorem. Tan chord theorem is about equal angles. They're not any particular size. Whereas angles in a semicircle is about angles in a diameter. So you have to have a triangle, a diameter, and if you have that, you have a standard 90 degrees always. The other theorem was the one where you have radii, which are extending from the center of the circle to form an isosceles triangle. And then you also have a line which is coming down, which is your line from the center of the circle to a chord will bisect the chord, cutting the chord in two. So over here you have a few reasons at play. You've got radii, which are equal, which are the size of an isosceles triangle. So it actually causes the isosceles triangle to exist. And if you have an isosceles triangle, it comes with equal angles. One pair of equal angles on the inside there. We also know that there's some congruency. Congruency meaning there's two triangles which are equal. And you have a chord which is bisected. Bisect means to cut into two. So we're bisecting a chord or cutting it into two equal parts. So we have a radii and which are equal. We have the two chords equal, and so we can end up talking about congruency. Congruency is when you have two exactly the same triangles, same size, same angles, but it's a different idea completely, and a topic which I don't think you're covering. Okay, so we've got the center of the circle, and we've got these two radii. We've got some isosceles triangles, which can form anywhere at any point in time. Because it reaches the center of the circle, extends a line to the center of the chord at 90 degrees, we can see that we have two right angle triangles on either side here. Because we have two right angle triangles, another idea that comes to mind is Pythagoras theorem. Because if you have, let's say this is 2, this is 3, you can work out the missing side. Where this is 4 and 3, you can work out the radius using Pythagoras theorem. You can go radius squared is equal to 3 squared plus 4 squared, and then it'll come to 5. So 9 plus 16 square root is 25, which is 5. And so the radius here would be a possible question that they could ask. And with Pythagoras theorem, remember you got three sides, so they can ask it in three different ways. They can give you the radius and a side, find the other side, or they can give you two sides and ask you to find the radius from there. Those are the main triangles in a circle theorems. And sometimes you could actually bring it all together into one in a particular example. Okay. All right. So that would be the first part that we did. So it's angles in a semicircle, 90 degrees. Tangent chord, remember, the angle between the tangent and the chord is the angle in the opposite segment. And then you got your angle from the center bisects a chord will be 90 degrees to the chord. And the reason here you could also say is angle from the center perpendicular to a chord bisects the